Section 7 of National Geographic Magazine, Volume 1, Number 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jimmy Lee. Report: Geography of the Air by A. W. Greeley. In presenting to the National Geographic Society a summary of geographic advance as regards the domain of the air, the Vice President finds a task somewhat difficult. The traveler passes from the east to the west coast of Africa, and his very efforts to struggle across that great continent impress in his memory an abiding picture of the physical features of the country over which he has passed, and of the distribution of plants and animal life. So, too, a vessel sails from one coast to another, casting here and there a sounding lead, from which measurements it is possible to give quite a definite idea of the relief features of the bottom of the sea. Small as are the traces which serve to indicate the character of the sea bottom, yet they are infinitely greater than those which enable us to give a description of the air. Atmospheric disturbances are so vast, and their action is so rapid, that it requires the attentive care of thousands of observers before one can well hope to draw the roughest figure of a passing storm. To note changes in the force and direction of the wind, to note the depth of the rain, the increase and decrease of temperature, and the varying changes of aqueous vapor, either in visible or invisible form, requires millions of careful, systematic observations. And then, when these are made, the task of collating, elaborating, and discussing them seems almost too great for any man. Fortunately, the value of meteorological work has impressed itself not only upon governments, which have assisted liberally by appropriations and organization, but yet more upon the isolated observer, thousands of whom over the face of the earth give of their time and labor, and add their mite to the wealth of universal knowledge. In connection with all great physical questions, there is at times a tendency to application to special phases somewhat to the exclusion of others. While it can hardly be said that scientific and theoretical discussion of meteorology has been unduly neglected during the past year, yet it is evident that the greatest activity of meteorologists has been devoted to climatological investigation, and compilations of this character have been particularly numerous during the past year, not in the United States and Europe alone, but throughout the whole world. The growing practical importance of meteorological researches has been lately evidenced perhaps in no more striking way than in the establishment in Brazil of a most extensive meteorological service created by a decree of the imperial government on April 4, 1888. A central meteorological institute under the Minister of Marine is to be the center for meteorological, magnetic, and other physical researches, and observations are to be made at all marine and military establishments in the various provinces, on the upper Amazon, in Uruguay, and on all subsidized government steamers. This service should soon be fruitful in results, as the meteorology of the interior of Brazil is almost absolutely unknown. Another vast scheme has originated in Brazil in the Imperial Observatory of Rio de Janeiro. Senor Cruels, its director, contemplates a dictionary of the climatology of the earth, giving monthly means and extremes of pressure, temperature, rainfall, wind, etc. This scheme, of course, can be successful only by international cooperation. The United States Signal Service has pledged its aid as regards this country. The former tendency among Russian meteorologists to devote their greatest energies to climatological compilations has gradually given way to other practical work in connection with weather and storm predictions, as shown by the institution by the Russian government of a system of storm warnings for the benefit of vessels navigating the Black Sea. Blanford has put forth an important paper which partially elucidates the very intricate question of diurnal barometric changes, particularly bearing on the relation of the maximum pressure to critical conditions of temperature, cloudiness, and rainfall. The question viewed in a negative light by Lamont as to whether the maximum barometric pressure could be attributed to the greatest rate of increase in the temperature of the air due, it is supposed, to the reactionary effect of the heated and expanding air, has been re-examined by Blanford, whose conclusions are somewhat in favor of this theory. S. A. Hill has treated of the annual oscillation of pressure so noticeable in India, and in doing so has investigated the changes of pressure for 3 levels, up to a height of 4,500 meters. The reduction of monthly barometric means at high levels, having regard to the vertical distribution of temperature, shows a double oscillation in the annual curve at the level of Leh, which becomes a single one at the height of 4,500 meters, while this is substantially the reverse at the oscillation observed below. The subject is also treated in another way by Mr. Hill through analysis of normal monthly means for all India, whereby he succeeds in presenting a formula, the first periodic terms of which represent the 2 principal factors of the oscillation. Mr. Hill has also discussed elaborately the anomalies in the winds of northern India in the relation to the distribution of barometric pressure. The anomalies are: 1. In the hot season, the wind direction frequently shows no relation to the barometric gradient. 2. The winds over the plains show little or no relation to pressure gradients, but an obvious one to temperature, being greatest where the temperature is highest. It is pointed out as highly probable that the copious snowfalls of the late winter in the northwest Himalayas not only produce low temperatures on the Himalayan ranges, but subsequently cause dry northwesterly winds over northern and western India, and on this supposition, reliable forecasts of the character of the coming rainy monsoons have been made for a number of years. Convection currents between upper and lower air strata, it is suggested by Köppen, explain diurnal variations in wind velocity and direction. At low stations, the maximum velocity occurs at the time of the highest temperature, while at high stations, the reverse obtains. Hill has examined into an important point connected with this subject, that is, the great local differences in the vertical variation of temperature. Hill concludes by saying that high pressures at low levels are the result of low temperatures, and in connection with the fact that wind directions are largely influenced by the irregular distribution of pressure at high levels, it is more important to know the abnormal variations of pressure at the highest hill stations in India than those in the plains. Overbeck has lately published a paper on the apparent motions of the atmosphere, in which he clearly and admirably outlines the treatment of the dynamics of the air by his predecessors. He comments on the mode of treatment of Farrell, as well as those of Goldberg and Mohn. Overbeck then sets forth his own method, and elaborately discusses the influence of the Earth's rotation with reference to the resistances which oppose the motion of the atmosphere. He touches on the effect produced by rapidly moving fluid entering fluid at rest, the development of discontinuous, so called by Helmholtz, currents, the tendency of parallel currents of equal velocities toward similar velocities, the effect of friction arising from contiguous currents of different velocities upon the coefficient of friction, of the temperature distribution over the surface of the earth, etc. He derives 3 very simple expressions for the motions of the air, the first giving the velocity in a vertical direction at any point, in terms of latitude, and a constant and factor depending on the distance of the point above the surface of the earth. The other expressions give the velocities in a north or south direction, and in an east or west direction, also in terms of constants and latitude. The velocity, when charted from Overbeck's equations, indicate an ascending vertical current from the equator to 35 degrees north, and thence a descending current to the pole. The meridional current at the equator and pole are 0, and have a maximum value at latitude 45 degrees. Ciro Ferrari, from long and important investigations of thunderstorms, shows that these phenomena invariably attend motionless areas of low pressure, and believes the surest elements for predicting such storms will be found to be the peculiarities in distribution of temperature and absolute humidity. He observes that the storm front invariably tends to project itself into the regions where the humidity is greatest, and that hail accompanies rapidly moving storms of deep barometric depression. Ferrari considers the chief causes of thunderstorms to lie in the connection of high temperature and high humidity. Grossman believes that ascending, moist-laden currents are the cause of thunderstorms, and hence they are most frequent when the temperature diminution with the altitude is very great, so that the overheating of the lower air strata in the warmest part of the day is the cause of the primary maximum of thunderstorm frequency. Abercrombie and Hildebrandsson have renewed their recommendations for a reclassification of clouds in 10 fundamental types, in which the first part of the compound name, such as cirrostratus, cirrocumulus, etc., is to be in a measure indicative of the height of a cloud. Hildebrandsson has charted the differences of monthly means of air pressure for January 1874 to 1884. In January 1874, the values at nearly all the stations in the northern hemisphere were plus, and those in the southern minus. It is to be hoped that such general discussions of this important meteorological element may be continued. General A. von Tillo has determined, by means of the planimeter, the distribution of temperature and pressure from Tilserenk-de-Bort's charts. The mean pressure over the northern hemisphere for January he finds to be 29.99 inches, 761.7 millimeters, and the temperature 46.9 degrees, 8.3 degrees Celsius. In July, 29,806, 758.5 millimeter, and 72.7 degrees, 22.6 degrees Celsius. In Russia, he finds an increase of 1 millimeter of pressure to correspond with a decrease of 1.6 degrees Celsius in temperature. Doberek, after investigation of September typhoons at Hong Kong, attributes their appearance to the relatively low pressure then existing between Formosa and Lyon. The valuable and elaborate investigation of American storms by Professor Elias Loomis has been completed. Loomis has thoroughly discussed barometric maxima and minima areas as presented by the maps of the Signal Service, from which it appears that these areas are in general elliptical, with the longest axis nearly twice that of the shortest in the high areas, while the difference is less in low areas. He has also investigated the winds relative to baric gradients, thus affording valuable data for proving various meteorological theories. Loomis's researches regarding the movement of maximum areas verify those which have been set forth from time to time in Signal Service publications, wherefrom it appears that high areas have a more southerly movement than low areas. Van Bezold has put forth a memoir on thermodynamics, while Helmholtz, Overbeck, and Dirokitso have contributed valuable memoirs on motions caused by gravitation and the varying density of the air. These furnish meteorologists with important results as to the laws of fluid or gaseous motions. It is gratifying to Americans to note that the valuable results obtained by Ferrel in his many memoirs are confirmed by these later investigations. Undoubtedly, the most important meteorological event within the past year was the discontinuance on January 1, 1888, of the system of international simultaneous meteorological reports inaugurated in accordance with the agreement of the Conference at Vienna in September 1873. As the charts of storm tracks based on these observations have been published by the United States Signal Service 1 year behind the date of the observations, the completion of this work in printed form for the general public should occur about December 31st, 1888. A few remarks in connection with this unparalleled set of observations may not be out of place. The Congress which agreed upon this work met in accordance with invitations issued by the Austrian government in September 1873. The cooperation decided upon at this Congress took practical shape January 1, 1874, at which date one daily simultaneous report was commenced from the Russian and Turkish empires, the British Islands, and the United States. The energetic cooperation of these nations being assured through Professor H. Wild for Russia, Professor A. Cumberry for Turkey, Mr. Robert H. Scott for Great Britain, and Brevet Brigadier General A.J. Meyer for the United States. Concurrent action followed shortly after on the part of Austria through Professor Karl Jelinek, Belgium through Professor E. Quetelet, Denmark through Captain Hoffmeyer, France through Messrs. U. J. Leverrier, Marie Davy, and St. Clair de Ville, Algiers by General Ferre, Italy by Professor Giovanni Cantoni, the Netherlands by Professor Buys Ballot, Norway by Professor H. Mohn, Spain by Professor A. Aguilar, Portugal by Professor F. D. Silveira, Switzerland by Professor E. Plantamore, and the Dominion of Canada by Professor G. T. Kingston. Within a year, the average number of daily simultaneous observations made outside the limits of the United States increased to 214. Later, the cooperation of the governments of India, Mexico, Australia, Japan, Brazil, Cape Colony, Germany, and Greece was obtained, and also of many private observatories at widely separated points throughout the Northern Hemisphere. In the 16 years during which simultaneous meteorological observations were continued, reports were received from nearly 1,500 different stations, about one-half being from land stations, and the others from vessels of the navies and the merchant marine of the various countries. The total number of storm centers, counting one for each 5 degrees square, over which the center has been traced from the international simultaneous observations of 1878 to 1887 inclusive, aggregates over 42,000, an annual average of over 4,200. Less than 1/25th of 1% of these storms occurred south of the parallel of 10 degrees, and only 1/4 of 1% south of the parallel of 15 degrees. In marked contradistinction to this freedom of the equatorial regions from storms, there is to be noted the excessive prevalence of these phenomena between the parallels of 40 degrees and 60 degrees north, in which region substantially 2/3 of the storms of the Northern Hemisphere occurred, while between the parallels of 45 degrees and 55 degrees north, 36% of the entire disturbances are recorded. The most remarkable belt of storm frequency on the Northern Hemisphere is that extending from the Gulf of St. Lawrence westward to the extreme end of Lake Superior, as nearly 8% of all the storms of the Northern Hemisphere passed over this limited region. The maximum frequency, 1.2%, occurring over the 5 degree square northeastward of Lake Huron. As regards longitudinal distribution, an unusually large proportion of storms prevailed between the 50th meridian and 105th meridian west, 37% or 1/3 of all the storms of the Northern Hemisphere occurring within this region. A second belt of comparative storm frequency obtains from the meridian of Greenwich eastward to the 30th meridian, over which region 15% of the entire number of storms occurred. Only 400, or less than 9% of the entire number of storms, entered the American continent from the Pacific Ocean, while about 1,300 storms, excluding the West India hurricanes, passed eastward off of the American continent. Over 900 storms entered Europe from the Atlantic Ocean, of which probably 450, or 10%, of the whole number recorded were developed over the Atlantic Ocean. Probably not 30 storms, or less than 3%, of those which entered Europe from the Atlantic crossed over the continents of Europe and Asia to the Pacific Ocean. Fully 2/3 of the storms which entered Europe from the Atlantic are dissipated as active storm centers before they reach the Asiatic frontier. The tendency of great bodies of water, when surrounded wholly or largely by land, to generate storms or facilitate their development is evident from the unusual prevalence of storms over the Great Lakes, the St. Lawrence Bay, and the Gulf of Mexico in North America, over the North and Baltic Seas, Bay of Biscay, and the Mediterranean in Europe, the Bay of Bengal, and over the China and Okhotsk Seas. Undoubtedly, a considerable proportion of these storms are drawn towards these regions owing to the effect of evaporation upon the humidity and temperature of the superincumbent atmosphere, so that a very considerable proportion of the storms credited to these squares have not originated therein, but have been drawn up from neighboring quarters. This tendency is marked in North America as storms pass over the lake region and St. Lawrence Valley, whether they have originated in the Gulf of Mexico, along the central slope of the Rocky Mountains in the United States, or further north in the Saskatchewan country. In like manner, storms pass southeastward to the Mediterranean from the Bay of Biscay, and northeastward from the Atlantic Ocean to the same sea, and then later show a very marked tendency to pass over the Black and Caspian Seas. This tendency of storms originating in diverse sections to move toward the lake regions in the United States is very evident from the normal storm track charts for April, May, June, August, November, and December. The opinion that gales rarely, if ever, occur upon the equator is confirmed by these storm tracks. The most southern storm in the North Pacific Ocean developed in July 1880 between the island of Borneo and Mindanao, an excellent account of which is given by Père Marc de Chevrens, S.J., in the Bulletin Mensual of Zai Kawei Observatory. The most southern storm over the North Atlantic Ocean in November 1878 was remarkable for its origin, duration, length of its path, and its enormous destruction of life and property. It was central on the first as a violent tropical hurricane near Trinidad, the barometer being 29.05, the lowest ever recorded there, and from its intensity and velocity, it is more than probable that it originated considerably to the eastward and possibly somewhat to the southward of that island. The storm was described in the U.S. Monthly Weather Review for September 1878. The writer looks with considerable interest to the results which may follow from a discussion of the annual fluctuations of the atmospheric pressure as shown by the mean monthly pressures deduced from the 10 years international observations. As far as these means have been examined, they show that the periodicity of atmospheric pressure is largely in accord with the results set forth in 1885 in the report of the Lady Franklin Bay expedition. The conviction expressed in that year is still adhered to, that at no distant day the general laws of atmospheric changes will be formulated, and that later, from abnormal barometric departures in remote regions may be predicted the general character of seasons in countries favorably located. The success of long-time predictions of this class for India has been set forth in a previous part of this report. It is believed that a further discussion of meteorological phenomena on a broad basis by means of international weather charts, both in daily and monthly form, must eventually result in important and fundamental discoveries. It is gratifying to American pride to know that in this international task of outlining the geography of the air, the United States has liberally provided the labor and means for presenting these 10 years meteorological data in such tabular and geographical forms as to render them available for study by all. Acknowledgement is due to Professor Thomas Russell for valuable translations, especially from the German, which translations have been of material value in preparing this report. December 1888. End of Section 7. Recording by Jimmy Lee, San Francisco.